Good morning, good afternoon, good evening, depending upon when you watch this. I want to talk to you today about what we mean when we talk about normal data. And an example would be, let's suppose our data is heights of U.S. adults. Now, what do we mean if we're talking about, so our data set would be height of adults measured in inches, measured in centimeters. The units don't matter, but consistent units, of course. If the data is normal, then when we look at a histogram of the data, our histogram would be something like this, and don't get too hung up on what this looks like. This is a sketch. I mean these to all be the same width, not different widths. So this is what normal data would have a histogram resembling. I would have a few people that were on the short end here, not too tall. And I would have a few people on the pretty darn tall end. And most of us would fall right here in the middle. The mean of this distribution is going to be right about here somewhere. We use X bar, X with a bar over it. I'm going to just correct that for a second, because I'm talking right now to you about the population of all U.S. adults. So that would be my population. And if we're talking about the population, same concept, the mean, but we use a Greek letter for it. We call it mu. So let me just stick a mu in here in the center. So the average that we call mean would be right here in the middle. Now, of course, a good question is, if I'm asking you the question, is the U.S. height data normal? Well, that's a question not unlike the average weight of feral hogs in Texas that we talked about. You really would have a heck of a problem getting hold of all height data for U.S. citizens. So to answer my question, what you would do would be to take a sample. So you want to take a sample. You want to be sure it's representative. And of course, the probably easiest way to get a representative sample is to be sure you take a random sample. It's feeling good. We got a lot of words that we know now because we've been practicing vocabulary, so you've got some idea what I mean by that. So we would take a random sample, and it would have to be good size. And usually with samples, bigger is better. And if you've taken a representative sample, you could look and see if the sample data is normal. Does the sample data, I'm going to say, appear to be normal? Well, I'm going to take you through today then a couple examples where we're going to try to answer that question for ourselves. Maybe first of all, though, just a word about why is that an important question. And that's an important question because most of the techniques we're going to teach you in the rest of this class, in one way or another, depend upon the population that the data came from being normal. And that's going to be true when we do hypothesis testing, when we do regression, when we do well, if we get to analysis of variance, ANOVA. So most everything that we do depends upon having underlying normal data, and there are ways to check that, and they're not real difficult, and that's what we want to look at today, some ways to check that. So a first way to check would be to look at the data in a histogram. And if the histogram resembles this kind of a picture, symmetrical distribution, and the right-hand tail and the left-hand tail look like they're just about mirror images of each other, that's good visual evidence that what you have is a histogram of a normal population, data that came from a normal population. Now, sort of 1A would be to put a normal curve over the histogram. That would help you visualize how normal the data really is. Now, if I had perfectly normal data, I could draw a continuous curve that would represent that perfectly normal data, and it might look like that. So it will help me judge how normal the bars are if I have the perfect normal continuous distribution over the top. So that's 1 and 1A. 2 would be the empirical rule, but because I haven't defined standard deviation for you, I want to hold the empirical rule for a few days, and then we'll do the empirical rule. But because these are so easy with Minitab, number 3, and this may be the best way yet, is to use the Ryan-Joyner test. And we're going to do those. And I don't think there's any better time to do those than right now. So let's see if we can get our copy of Minitab up. Well, fortunately that happened pretty easily. So here's our copy of Minitab, and I have this file that we've looked at briefly a couple times before with heights in them. Now these heights are in centimeters, but it doesn't matter. Changing the variable will not change the shape of the data. It will change its location left or right, but everybody the same amount, but it won't change the shape. And so we'll work with these heights that are right here. And we said if we want to know, is heights in the US normally distributed? Well, is this sample of size 300 normally distributed? So let's go up to graph, and we're going to draw a histogram, and we're going to make it just the simplest histogram, so it'll be this guy right here, and we'll say OK. And then what we want to look at is height, and that's what's selected already, so that part's good. Labels. Let's make our label be height, adults in USA. And we'll just, units are in centimeters. All right, so now we've got labels, and we'll say OK and OK again. And here is our picture, and let's squish it a little bit so that it fits nice. And there's our picture. And then the question would be, is that normal data? Well, let's see what argues that it's normal data. What argues that it's normal data is it builds to a center and then it falls off. Now, if I was going to call this perfect normal data, I would think that we would want to build a little bit slower to the center from the left so it would look more like the right. But, that's not horrible. That's not real bad. This is characteristic of a pattern where we may have some underlying variable that's making height different. Like it looks like over here on the left, it looks like I've got a normal distribution where this is the average height right in here. And on the right, it looks like I've got a different normal distribution where this is the average height would be about here. Now, why in the world would that be if these are adults in the U.S.? Well, I think gender could be a variable that would give me two different distributions of height because men tend to be a bit taller than women. Let's put a normal curve over this as the next step. So let's go to Stat, Graph, Histogram, and this one would be with a normal curve smacked over the top, and so let's say OK to that. And I think everything else is OK here, so we can leave that the way it is, and we'll get a new curve. And how does that look? Well, now you can see that while not perfect, the red line is the perfect normal curve. The blue's not too far off, is it? Not too bad. A little too much down here, a little too much here, not quite enough in here, a little bit too much over here, but pretty dang good, about as good as you can expect. So I would not hesitate to say that that underlying data is behaving as though it were normal. I would not, if I had a hypothesis that the data was normal, I would not reject that hypothesis based on the evidence of this sample of size 300. Since we're here, let's look at a histogram where we break out male and female. And that's what these icons down here are doing. This would break out male and female. This would break out male and female, but impose a normal curve on each of those subpopulations. So I really think that would be interesting to look at. Now, what would that be? What would we do? Well, for the graph variable, we'd select height, and you can see that's already been done. I did that a few minutes ago. So I came down and selected height off the list to the left, and selected down here or double-clicked. Either way works. The categorical variable for grouping is going to be gender. And a label, probably should put a label on this. We know we should. We always put on a label. So let's say male and female height. And for a subtitle, let's say U.S. adults. And for a footnote, let's stick my initials on it. And we'll say OK for the labels, and I think everything else we don't have to look at, so we'll say OK again. And let Minitab generate this graph for us. And I'm going to small it up so it fits a little better. I'm going to small it up just a little bit more. Okay, so here's what we've got. This is so easy to make and such an interesting graph. The blue would be the gender female. The red would be the gender male. And so the material on the left is primarily blue, primarily female. And if you just look at this blue perfect curve, you see that the blue bars, and they're this kind of deep rows where they overlap because I've got two colors peeking through here, but you can still see that these would be the females. And boy, they fit that normal curve pretty well. Now the red dotted would be the perfect curve for a normal distribution with the same average value as the males in this sample. And A little bit short in here, but all in all, pretty darn good. So it looks like our surmise that maybe this height data had two different variables in it, female height and male height. It looks like that's kind of supported as we look at the two histograms overlaid on the same axis. Now, in the interest of time, I'm going to jump right over to a test of normality called the Ryan-Joyner test. And so stick with me here. Let's go to Stat and Basic Statistics and come down to where the bottom, and there's Normality Test. These are tests that test whether a data set is normal or not. And they're very powerful and they're very useful. So what does this look like? We've got to see what variable we want to test, and I've got height already keyed in there. Now, later on we'll talk about what the percentile lines are, but we don't need percentile lines right now, so we'll just leave that alone. None is the radio button that's checked. Test for normality. There are three, and you can pick any one of those, and they're similar. And many people use Anderson-Darling, and I did for years, but now I like Ryan-Joyner a little bit better. This is kind of like, do you like pumpkin pie on Thanksgiving or do you prefer pecan pie? They're both really good, aren't they? We're going to do a Ryan-Joyner test, and so I've got this radio button checked, and we can put a title on our graph. So this is going to be height U period S period ADULTS, adults. Just because I harp at you about putting titles on your graphs, I want to try to remember to do it myself as well. And now let's scrunch this down sufficiently to fit in a nice window here. And here's how we read the Ryan-Joyner test. This has got a straight line, red line. It's covered up most of the way, but a red line all through this graph. The blue dots represent data points, and so we know we've got 300 data points in this data set, so there would be 300 blue dots. If the data were perfectly normal, all the dots would be on the red line. You can hardly expect that. In real data will not be that normal. But most of the dots here are on that red line, and they really are very, very faithful about getting down to that red line. A little bit big out here, and this would be the high values of height. And we got somebody that's really short down here. But for the most part, I have no trouble saying, wow, that indicates normal data. And there's one other thing that I'd like for you to look at, and that's this little box up here in the right-hand corner, upper right-hand. This tells me that the mean for these heights was 168 centimeters. That's just maybe handy information. And we haven't defined standard deviation yet, but it's a measure of the spread of the data. And that has a value of 9.58 to round it. And this reifies that we did have 300 pieces of data. We knew that. It's nice to have confirmation. This is the value of a Ryan-Joyner statistic, which we don't need right now, but this is an important value down here. The p-value kind of measures our surprise or lack of surprise at how well this data fits. And we've got a hypothesis that the data set is normal. That's the hypothesis that we start the Ryan-Joyner test with. If the p-value is less than 0.05, we would reject that null hypothesis. And p-value less than 0.05, we would say, it doesn't look like this data is normal. I can't support that this data is normal given the evidence I have from this data set. But we've got a p-value that's greater than 0.1, so it's getting quite a bit bigger than 0.05. we cannot reject the hypothesis of normality. It looks like the adult heights have normal height. Well, I'm going to quit here because this has gone on long enough, and we will talk in the very near future, and maybe we'll get some cases here where the data is not normal, so you'll have that experience. We want to get into what standard deviation is and look at the empirical rule, so we've still got lots of statistics to do. But meanwhile, thank you very much for your close attention here, and have a good weekend.